Hello, welcome, and an excellent evening to you folks. Today we are back again with a Let's Code MS-DOS episode. It has been a while and I still have some open things to tackle here, but today we are doing something different. We're doing a nice graphical effect that is probably known to a lot of you. It was in quite a bunch of different demos and some games might have used it. And I thought, well, it's summertime and here at least it's pretty hot. So let's do something high temperature as well. And let me just show you what we are dealing with. This is a fire effect. This is supposed to be a nice fire, and as you can see, it is not running extremely fast, because the fire effect is actually pretty expensive to compute, and this is already a fast version in quotation marks running on my 486 at the moment. On the 286 it would be quite a bit slower, maybe 1 or 2, I think, frames per second are the best that you could hope for. I mean, even here it's only just like 2 frames per second probably. So on the 286 it's more like 2 or 3 seconds per frame, I guess. Because, I will explain to you the algorithm in a very short while, but yeah, it's expensive. And we already did some optimization here, and we can do better actually. Of course, we're using Turbo C, so in assembler it could be faster. Using 386 opcodes could make it faster, but I want to target older and slower machines, and I want to teach it in a bit more higher level language like C. We can at some point convert this to assembly, of course, and we will come back to assembly Let's Code as well, because that was actually pretty popular. And yeah, but this is the version that I did first, just to show that it works. But then we will have a look now at something that is even faster, with a bit of trickery from the VGA card. Because, let's face it, the fire doesn't need that many pixels because it's quite blurry, and it's much nicer to have it running in a high frame rate actually. And while the VGA card can't do real scaling in X and Y directions, like for example some dedicated hardware could, we have a few tricks on the card that help us with getting something akin to scaling, not arbitrary scaling, but by a factor of 4, and that should help us with the frame rate quite significantly. So I'm going to load up a different program where I will walk you through the program itself. We are basing this on previous episodes, so the types.h and vga.h header are actually known from previous episodes. If you haven't watched those, you can go back and watch them first. I will switch to a different Turbo C project. And I've also included here a header file called pal.h, which is the palette, because I don't want to talk about how to create the palette for the fire. I honestly ripped it off of another example program of the internet. It's just 768 byte values which encode the nice fire colors, but you can choose your own palette or generate it using some for loops, which I usually do, but that's not the topic of today. Today we want to make this faster, and we are going to use mode X or mode Y, or a variation thereof. So we will use the functions that we introduced in the VGA header last time, but we will also use a frame buffer, which is located in system memory, because our trickery will depend on that, and reading and writing to system memory is usually faster than to the actual VGA card. So that we will have, and we will need some set pixel and get pixel macros into the frame buffer, which are very simple. These are the same as for the flat 13 hexadecimal mode of the VGA card. It's basically just the frame buffer address plus the screen width times the Y coordinate plus the X coordinate. Make sure if you use macros like I did here, because I didn't want to depend on inline functions working in the compiler, to put your parameters into parentheses. Otherwise, if you have some calculation in there or some other stuff in the original variable, this will get put in there as well. It might lead to problems later down the road. We need 3 functions, the draw fire routine, the draw fuel routine, and the main function, because the fire effect works like this. In a loop we will always draw new fuel, that is on the bottom of the screen we will draw white pixels, and they will be the hot burning coal, and then the draw fire routine will go from scan lines, from all the scan lines from top to bottom, and compute a blur basically of the 3 scan lines below and average them out, which generates an upward motion at the same time as making the fire more and more blurry the higher you go up the screen. And this is basically using some linear filter. You can express this as a matrix or a filter kernel, but it's actually a very primitive one, and we will already optimize this as to reduce the number of operations that we actually have to calculate. But let's go top to bottom. Let's write the main program first and then go to the actual implementations of the other functions. So the main functions, we need a few variables. We need something to encode the fuel intensity, and because we want to have a nice effect there when we quit the program. So initially we use 255 as our highest intensity for the fuel, and I will need a helper variable for the fuel only for quitting the program. You can ignore that for now, I will explain it in a short while. Then we need an iteration variable usually, and that is actually it, I think. I think we don't need anything else. And then we need to call the randomize function, which is turbo C specific. It will set the random number generator to something useful and generate a different random pseudo random number sequence every time you call it, because it's time based. So we get a different fire each time we run this thing. Then next up we will set the graphics mode. We will switch to mode Y, which is 320 by 204 video pages. If you don't know about that, check out my earlier videos. I explain how it works and what the advantages are of this graphics mode. Then we set the palette to what was given in the header file that I just showed you. So we have the nice colors, and we also need to allocate a frame buffer, and the frame buffer will simply be our screen width times screen height. Just like that. Make sure to use some larger memory model. Using compact allows you to allocate stuff on the file heap by default, and that will be much simpler. So that's that. Next up we will check, just a sanity check, if frame buffer is null, then something bad happened. So we will print an error message. Not enough memory or something. Should never happen, except you're maybe running this from inside Turbo C and you're very low on memory to begin with, but actually I don't think even then, because we use very little memory here. But better safe than sorry, and for bigger programs or games later on this will be useful as well. Then we need to clear the frame buffer, otherwise we see a lot of garbage on the screen. So we set the frame buffer contents, can't see my keyboard, to the value 0. You can also play around with different stuff, but that doesn't make much sense. We clear the whole screen, and that's that. And then we can do an endless loop, or more or less endless. It of course has an end. And usually I would write here while not keyboard hit. And in the end we switch back to set text mode. But we won't do that today. Instead we will do something different. We will look here if some keyboard key was pressed, if keyboard hit. Then we first of all clear the character that was read, otherwise DOS might read, for example you press enter, DOS might read that and press enter on the command line, or if you launch it from the Norton command or something, it will launch the program again, and that's pretty annoying. And now here comes in my helper variable. I will set this to, this is supposed to be delta fuel. I will set this to 5, and my while loop now will be as long as our fuel intensity is greater than my delta fuel. And the idea will be here that every frame we subtract delta fuel from the fuel. While you're not hitting any key, this will stay 255, but when you hit a key it will slowly fade out by decrementing the fuel amount until it's 5 or less, maybe even 0, but you can put in any value here. Putting a higher value in here will fade out faster, and that's a nice effect for stopping the fire actually. Then, after we dealt with the keyboard stuff, we can actually draw the fuel, and the function takes some rectangle where we want to draw it, and we will say go from the top left, which actually isn't that important because I shouldn't have used a rectangle because I only draw the bottom line. One coordinate and the width should have sufficed, but there we are. It is what it is. I will write 80 pixels horizontally and 52 vertically. Normally I would use 50, and let's put that here as well, but we'll change that later to 52, and you will see in a minute why we're doing that. And then we also call draw fire, and draw fire takes a true rectangle now, and I will put it to the same size for now, and it will also be changed to 52 for some reason later, which is a minor reason, but I think it looks better. After we drew the fuel and drew the fire into the memory frame buffer, it's not yet visible, so we wait for the vertical retrace of the screen, so that when we do something now there will be no screen tearing and you can't see until the retrace is finished. And we will use a new function that we still have to write called blit4. And blit4 will basically scale the image by a factor of 4 in both directions, and it will be a very fast blit. So it takes the frame buffer as its source, doesn't need any destination except for the rectangle which we want to use, and it's basically the same. This is the size that we want to copy. We can copy just a subset of it if we want to, but no need for that. And this will be the function that we will look at last. But first we will take a look at the fuel function because it's simple, and the fire function because it's interesting how the fire is actually being drawn. So let's have a look at fuel. Fuel is rather simple. We actually need an iterator variable, and we need a temporary fuel variable as well, and then we can iterate, and we start by going to the first corner, x and y. Actually, we don't need the y here, but we initialize I with x, and as long as I is less than x plus the width, we can increment I. That means we run from x to x plus w, which is the width. Then we calculate the actual fuel, and we make the fire flicker by using random fuel values every frame. And we get the random value by computing something, converting it to a byte, and that something is a random number. And since we only need a byte, we only take the lower 8 bits, which can be done by using the bitwise AND and masking it with 255. You could have written 255, or more easily, I think, 0xF. Yeah, this selects only the lower 8 bits basically. And then we check if this value is bigger than 128, which is 0x7f. And if that is the case, we pick the current fuel value, otherwise we pick 0. This gives us a nice effect that we have more flicker in the fire, because the fuel can either be on or off and nothing in between. If you just use the random value here, you get a much smoother fire without much turbulence. And this here, I think, looks better, but you can play around with this line and produce different fire effects. You can even draw text or something. You can draw circles and let them burn, or I don't know. You can play around with this, or 3D objects you could use. This is basically what you want to light on fire, and the draw fire is the actual filter basically. Okay, since we selected that, we can use the setPixel macro to write into the off-screen frame buffer, and we use I as the x coordinate, and we use y plus h, and that's why I said we don't need actually both the coordinates, because it's always the same, and the temporary fuel value. And that's our draw fuel. Pretty simple. Now comes the draw fire routine, which is a bit more interesting. And yeah, in theory, what we need is something to collect the color in. And sorry for the noise outside, but I actually can't close the window today because it's too hot. And we also want to have our filter kernel, which I call O. I don't know why, but I did. And it's of size 3x3. And to make sure that it has sensible values to start with, we initialize it with all zeros, and we can just write it down. We don't need any memset, which would be an overhead. And in a second we will use this here as well, another array of 3 values, which we also initialize with zeros, but we won't use it straight away, but in a second, as I said. And we need some iteration variables. We will use them later. And then what we'll actually do is we will iterate over the x and y directions. Y direction will be first, so j will be our y iterator. We start with the y coordinate, obviously, and run up to y plus height and increment. Same goes for the x coordinate. So this is basically processing every pixel on the frame buffer. And so there's not much to explain here. It runs scan lines from top to bottom, as I said. Goes from 0 to 200 in our case, or 250, because we are drawing at a quarter size to make it faster. And yeah, actually what we would now do is we would now take all the pixels. Let's draw it like this. We would take all the pixels, and this would be the current pixel that we're looking at, and we would take all the pixels that are below it and next to it, but not above, and average them and make basically a big sum of those and divide that by 9. Yeah, okay. But that's expensive, because you would call getPixel on all these things, and that's pretty expensive. And also computing the sum is pretty expensive. So instead, what we are doing is we note that from pixel to pixel, we only ever need to get 3 new pixels. And these are these ones here. Because when we step through the screen, we're going from left to right. Let's draw it like this. We're going from left to right, and there will be 1 additional column of pixels that we need to get. These here are the same from the last iteration. So we can first of all store these and also pre-compute the sums. And yeah, that's actually pretty useful, I would say. So we will only use that, and this will give us a speed up, not a huge speed up, but something like 50% or something, or yeah, a doubling roughly. So let's do that. First of all, we need to compute some index, which are called dx here, to make the O kernel be more or less a ring buffer, and this will be the I coordinate modulo 3 times 3, which means we will at first, because then you can also leave out the sums. The sums can be added later, and basically in the first iteration you will write to this triplet, then in the next iteration we will write to this triplet, and the others will stay the same. It will become hopefully a bit more obvious. Basically what we'll do is we write to O dx plus 0, and the plus 0 is not necessary, but it's for visualization purposes for you, the value that we read from the pixel, and the pixel is the one in the column to the right, that's I plus 1, and in the current line, so j plus 0, and oops, sorry, then the next 2 values are basically also the column to the right, but 1 line down. And that is basically the update of our filter kernel. And in theory, we could now just sum over all the filter kernel values and be done with it. But actually, I will skip that, and actually noticing that we can actually live with only 3 values here for the filter kernel. I needed the 9 values. Now let's write it. Let's write it that way, so that we need the 9 values. Actually, what you can now write is C equals O of 1, O of 0 plus O of 1, and etc, etc. I won't do a loop here, because a loop is actually more expensive. So let's do it like this: 3, 4, 5, 6, 7, 8. And the most simple thing to write here is just divide by 9, which averages everything. And then we're doing one more thing. We are actually attenuating the fire. So we take the maximum of this value and 2, because we don't want to produce any negative numbers, and subtract -2. If you don't do that, the fire will grow higher and larger. You can attenuate it by writing arbitrary values here, but I found 2 to be a nice effect. And then we can actually set the pixel and write that to the position ij with the color C. So this is already much faster than the naive solution, which uses 9 getPixel calls. So this is quite a bit faster, but we can still cache the partial sums here. And when we do that, we don't need the whole 9 values anymore, and we don't need to compute this index here, but I leave it in so that you can check. So we're gonna comment this out by doing the if0 trick, so you can switch between the implementations and see the difference. And what we'll actually do here is we will use the S array, again with the I modulo 3 to get a ring buffer, and then we simply again take the values that we just computed, O dx plus 0 plus O of dx1, and here you can already see that we actually don't need the whole buffer anymore. Let's actually optimize it. Let's put this in here and make this much simpler by using O of, actually no, we make one large, let's make one large expression because we can. We're gonna take this and we just add up all the pixel values straight away. So these are the neighboring pixels, we don't need to store them anymore, and this should be our whole expression, right? And then what we can do is we can just sum up the 3 values that are in the sum vector and divide that by 9, and that should be the same as the whole clutter above. And I think this is pretty neat. This should give us quite a bit of advantage, because let's face it, TurboC will not be intelligent enough to optimize this code to this code basically. A newer compiler probably can do that, yeah, but if we would hand code it in assembler, we would do it in a similar fashion. So yeah, I think there's still some leverage in assembly coding, but this will be quite nice already. So this is actually everything in the Fire program. It's not large, it's 80 lines with roughly 20 lines of boilerplate at the top. So it's a pretty small algorithm, and this is just alternative code, so you can even scrap that. So yeah, let's implement the VGA blitting routine, because that's still missing. And I'm just gonna walk you through this to save a little bit of time. This is the blit4 function, and it's similar to the blit function that we already had. There's a blit to page function that we used, which copies all the 4 bit planes one by one, and this gives a pretty fast blitting routine. It's not perfect, and it wants the pixel data in memory to be aligned in the same fashion as mode X, that is, every other pixel needs to be on a different bit plane. And this is not the case with our blit4 routine, but it looks similar. We first of all write to the map mask register, and we don't have the loop over the bit planes anymore because we want to write to all the planes at once, which means every pixel that we write gets multiplied by 4. So with every write, you actually write 4 pixels on the screen. We compute the bitmap offset as usual, set it to 0. The screen offset is simpler because it's just an index into the VGA memory divided by 4 due to the multiply by 4 with the bit planes. And then we iterate over all the lines on the screen, and we simply copy 4 times every line and update our screen offset in every line but update our bitmap offset only every 4 lines, because in the horizontal direction we get the scaling for free, and the vertical direction we have to do a mem copy for every line. And that's already the whole trick to get like a free horizontal rescaling. More than factor 4 is not possible, I think, but you can do a scaling by 2 by writing to 2 bit planes at once, 2 neighboring bit planes. You have to adjust it here, and then you have to loop over 2 bit planes. Then you get a free scaling by a factor of 2 basically, which is nice because it will get you a less chunky look, but for the fire I think this is pretty nice. So let's see if we can compile this. We got 2 warnings. The DX is not used. Yeah, we should probably put that into the thing here, and O is also never used, but we don't care about that right now. This is for the alternative code, because O is actually not needed anymore, but that's fine. It doesn't hurt the program. And yeah, here we go. And as you can see, it is a lot faster than the original program. And now you can also see why I wanted to push down the fuel by 2 lines, because I think the bottom 2 lines actually look a bit too flickery. And when I press the key, you will see the fade out effect, which I think looks very nice. Let's actually push down the fire by 2 pixels. The blitting stays the same because we don't have any more space on the screen, and I think this looks a bit more smooth, but that's up to you. You can change it as you want. Yeah, and this is a very nice chunky fire effect, and you can use the split function for all kinds of things. I think some rotozoomers might have better performance if you compute it on a more coarse resolution, for example. Yeah, and that's already it for today. I will put all the source code on GitHub, including the Mode Y version, which is pretty slow, and I will actually try to incorporate the optimization that we just did by leaving out the whole O array, and yeah, because that should be the fastest version that we can get and see, more or less. If you have some improvements, please share them. You can fork the GitHub repo, play with it. And other than that, if you haven't subscribed, please do. It helps a lot. Give it a thumbs up, this video, or a thumbs down, depending on if you liked it or not. In any case, leave a comment. We can have a nice discussion always. And if you want, you can also support me. There are a couple of patrons who are already supporting me. You can head over there. You can also head over to Ko-Fi and buy me a coffee, which is also very nice, or PayPal me something, which helps me to spend more time on this and less time on other work that you can't see, which would be a nice thing. And if you can't do that, it's also fine. I'm happy that you watch this stuff. I'm having fun doing this. And I hope to see you in the next Let's Code video, or rather in any video that I make. So have a great evening.